Okay, so it's my pleasure to introduce Ciprian Manolescu from UCLA, and he will talk about triangulations and manifolds.
Thank you for the invitation to speak. So I will talk about different questions related to how to present manifolds in a combinatorial way. So many of the spaces that we encounter in topology have, first of all, we'll focus on manifolds, things that are smooth, so locally look like Rn, and many of them can be expressed by gluing polyhedra. So, for example, the torus can be obtained from a square by gluing the opposite sides. And if you want, you can subdivide this some more. So you can, instead of having a square, you can just have triangles. And if you subdivide it even more, you get what's called the simplicial complex. This is just, it's determined by a set of vertices and then a set of simplices. So every time you have a pair of vertices as part of the data, you draw an edge, and every time you have three, you draw a triangle, and this is a combinatorial object. So that allows you to express the space in a combinatorial way. So if you want to do something with it, you can plug it into a computer.
So what was the problem when you had only two triangles? Or?
Yes, when you had only two triangles, they had just one vertex, and there were several edges from the same vertex to itself. So, but this one you can just write it as yes. So you want every simplex to be uniquely determined by its vertices. Yeah. So the first question along these lines was asked by Poincaré in 1899 in Analysis Citus 2. So Poincaré introduced both of these spaces, both of these kinds of spaces, manifolds and spaces obtained by gluing polyhedra. So in modern language, his question is: does every manifold, you are working with smooth manifolds, so smooth manifold have a triangulation?
I think smooth manifolds were defined by width.
Yes. No, I said translated into modern language.
So he actually did define.
He did it. No, so he was looking at spaces in Rn that are locally defined by the zeros of some smooth functions with a non-zero Jacobian. So does that have a triangulation? So by triangulation I mean a homeomorphism to a simplicial complex. And Poincaré actually attempted to give a proof of this, and it's there, but it's not rigorous, and it turned out to be not completely trivial to give a proof, so it took, I took until the 40s for people to write it down, but the answer is yes. So this is due to Cairns and Whitehead. Yes, so the answer is yes, and the main idea is that if you have something smooth, then smooth things you can approximate by linear things, by their derivatives, and then, this way you can make something piecewise linear. So that's the first version of the question, but here is a more difficult question, which was asked by Kneser in 1924. Again, in modern language, it says that does every topological manifold have a triangulation? So topological manifold is just a topological space that locally looks like Rn. There's no smoothness condition, and this turns out to be more difficult. People believe that the answer was yes, but it is not yes. And let me say a bit about the history. So this depends on the dimension. Let's say dimension n. So the answer is yes, for n less or equal than 3, in this case, there's actually topological implies smooth. And yes, it implies piecewise linear. This is due to work of Brado for surfaces and then Moise for 3 manifolds in the 50s. But it turns out to be no in the other dimensions. So for n equals 4, the first counterexamples were found. So in the 80s, Casson, Casson proved that, for example, Friedman's E8 manifold is not triangulable. So Friedman found some new constructions of topological manifolds that are not smooth, and then Casson developed his invariant, and with that we can show that yes, these ones are typically, they don't have triangulations. So the generic case is high dimensional, so n greater or equal than 5. And that's what I will talk about today mostly. So the proof has kind of 2 separate steps. So the first step was done by Galewski-Stern and Matumoto in the 70s. So what they showed is that you can rephrase this problem in terms of low-dimensional topology. So they reduced this to a question in 3 plus 1 dimensions. And I will spend some time explaining that. So whether non-triangulable topological manifolds exist in higher dimension, it's a question of a different question about 3 manifolds and 4 manifolds that bound 3 manifolds.
It might be useful, especially because we're on a floor called PL, to explain how this question is different from PL.
I was planning.
Okay,
Yes,
we'll get to that, right?
that's next. Yes, for sure. Yes, absolutely. So anyway, so I solved this problem 3 years ago. So this is the solution to. Solution to this using gauge theory. Oh, we're on a floor called PL. What is that?
Plaza level. There's no sign to say PL.
Good. So this is not going to be. So this is not one of the counterexamples. I could have just pointed to it, but I see. All right. So yes. So the next thing I also wanted to make the distinction to the third version of this question, which is it's a stronger question. There's every topological manifold have a PL structure, so piecewise linear structure, means that, it's an atlas of charts such that the transition maps are piecewise linear. So you can decompose them into simplices and get the linear on that. Equivalent, it turns out that this is the same as having what's called a combinatorial triangulation. So it's stronger than asking for a triangulation. A combinatorial triangulation is, this is kind of a misnomer, because all triangulations are, combinatorial data. But what people mean by this is the kind of triangulation where the manifold structure is apparent, in the sense that if you look at the vertex, and you look at all the simplices that contain the vertex, and then you take the boundary of that, this is called the link of the vertex, and you want this to be piecewise linear homeomorphic to Sn. basically it could be a sphere, I guess of dimension n minus 1. And if you have a simplicial complex where the links are spheres, then of course this is a manifold, because locally it looks like the cone on a sphere, which is Rn. So a combinatorial triangulation is something where it's like clear that the space is a manifold, but it turns out, so in a moment I'll get to examples where this is not true, even though you are in a manifold, but there are different kinds of triangulations. Let me just mention the history of this. So the answer is the same as before, but was found earlier. So yes for n less or equal than 3. In those dimensions, topological PL and smooth are the same. But no for n greater or equal than 5. So this was the work of Kirby and Seiberg-Witten. From the 60s, late 60s. So they found an obstruction so delta in H for Z match T. So there is a certain element in the cohomology of a manifold that you can define for all the manifolds, and the manifold is piecewise linearly found only if this element is 0. So that's great, and then also no for n equals 4. So this was the work of Friedman in the 80s. So for 4 manifolds, he found these examples of 4 manifolds that are not smooth or PL. Smooth is the same as PL in dimension 4. And then a few years later, so he showed that they're not PL, and then a few years later, Casson showed that they don't have any triangulations at all. So I should mention, I'm not going to talk about this, but of course this is related to the Hauptvermutung problem. So that is the question of uniqueness. So if you have 2 triangulations on the same manifold, do they have a common subdivision? So, I mean, you can ask this for spaces, and then, yes, Milner found the counterexample, but for manifolds, so there's a classification. So this is still this is also false. And then they're classified by H3 of MZ monkey. So this is also part of the Kirby-Seiberg-Witten theory. Okay, so one thing I promised is let me explain the difference between these two.
That's usually attributed to Sullivan stuff.
Oh, it is?
I think. How come? You might remember that. Anyway, he's not here today. So.
Okay, good. Don't tell us. Okay, maybe it's a solid one. Yes, I'm sorry.
I'm going to kill the video recording.
Alright, so let's, actually, I was planning to mention his name in a minute, in a different context. Okay, so, let's discuss, I wanted to explain that there exists, these non-combinatorial triangulations of manifolds. So the typical example, it's not clear that it exists. It took a long time to for people to understand this, but here is how one can construct an example. So you can look at, let's take M, a non-trivial homology sphere. With non-trivial functional group. So, for example, you can take the Poincare sphere, and we're going to take cones on all the simplices. So let's say it's triangulated. Take cones on the simplices in both directions. That gives us the suspension, so sigma of them, and this is some space. It still has the homology of a sphere one dimension higher, but it's not a manifold. It's not hard to see that it's not a manifold. If you take out this point, then a neighborhood is not simply connected, whereas in a manifold it better be simply connected. However, what you can do next is you can take the suspension again, so you get sigma squared of them. And this is actually homeomorphic to Sn plus 2. This is a non-trivial theorem. It's a double suspension theorem. It's due to Cannon and Edwards in various degrees of generality. So it's not trivial to construct such a homeomorphism. But if you believe that that exists, this is you get a triangulation of Sn plus 2. And that triangulation is not going to be PL, because if you look at the link of this vertex, the link is this whole thing, and that is this, which is not a manifold, so it's not a sphere. Okay. Great. Okay, so right. So this question about, this is maybe the more natural questions. Those triangulations are kind of weird. This was settled, in the 60s and then in the 80s. But then the high-dimensional case was left open for these things, and this is what I plan to talk about. So the last, the question of whether there exist manifolds in high dimensions that don't have any of these kind of triangulations. So I will, let me start by explaining the first step. Sorry, I just erased, but the first step was this work from the 70s that reduced it to a question in low dimensions. So first was the reduction. Okay, so let's talk about question 2 in dimensions greater or equal than 5. And first we're going to do the reduction to 3 plus 1 dimensions. So, great. So for that, let's say we had a triangulable manifold. So let's say Mn, n greater or equal than 5, has some triangulation K. So there is, so to that you can associate the following element, and this is holy one. C of K is the sum over simplexes of codimension 4 in K, the link of sigma times sigma. I will explain this in a moment. In H, yes, so this is in H n minus 4 of n. Take that to H, where H 4 of n. Take that to H. I will explain this in a moment. Yes. Right, so if we have a simplex of codimension 4, I mean, if we have any simplex, we can find a link for it. Just as before, you look at the simplices that contain it, and then you look at the closure and the things that don't contain that simplex. So what you get is something like this. It's basically the thing that goes around it. This is the link of sigma. If this has codimension 4, then this is going to have dimension 3. If you are in a PL triangulation, then where kind of near every vertex you have a sphere, it turns out that these things also are spheres. So they're just S3s. In general, you can show that the links are homology spheres. So, yeah, just some simple algebraic topology argument it tells you that this link is 3-manifold with the same homology as the sphere. So, yeah, it's actually S3 if K is PL. But we're going to keep track of what homology sphere they are, so we're going to sorry, let me what I meant. Okay, so we're going to make a chain of simplices. So we're going to take the sum of these simplices with coefficients in some group, and that group is going to be made of homology spheres. So this is and then this turns out to be a closed chain, and then it gives you a homology class. So what is this group theta 3H? This is the homological Cobordism group. In dimension 3, it's homology spheres, homology 3 spheres, modulo an equivalence relation where two spheres are equivalent, so y0 is equivalent to y1. If there exists some PL cobordism, that also has the homology of the sphere, so or the relative homology is 0. Basically, that looks homologically like a cylinder. So these are manifolds that look homologically like spheres, modulo cobordisms that look homologically like cylinders. So maybe I should say oriented. What else I should say? So this is PL. You can also think of it as smooth. PL and smooth are the same in dimension 4. And there you go, you form a group. Now, why did I insist on dimension 4? So interestingly, you can consider this in any dimension, but one can show that theta and h is 0 for n different from 3. So somehow this group is only interesting in dimension 3, and that's why we're looking at codimension 4 synthesis. Yeah, I think that the fact that it's 0 in higher dimension is related to the H cobordism theorem and the fact that it holds in higher dimension, but it doesn't hold in low dimensions. Alright, so okay, so why is it non-trivial in dimension 3? So, by now we know quite a bit about it, but we don't quite know what it is. We don't know what it is, but we know that it's non-trivial. The simplest way to see this is something called the Brocklin homomorphism. So there exists a map mu from theta 3h to sigma 2. It's a surjective homomorphism. The way it works is mu of y is the signature of w over a mod 2, where w is a spin smooth manifold with boundary y. And it turns out that this, the parity of the signature divided by 8 is independent of what the core manifold is A. So that's an invariant of y, and it turns out to be should be sent to this group, and it's rejected. So, for example, mu upon rest here is 1. Oh, and I forgot to say, so this is a group, so addition is connected sum. You can change the orientation and you get minus, and S3, the class of S3 is 0. So, right, so let's keep, so basically we're keeping track of the simplices, of the links of simplices up to homology cooperation.
But is this group much bigger than this?
Oh yes, good question. So let me tell you what's known. So yes, actually I wanted to end with some open problems about it, but it's known that theta pH has a C infinity subgroup, and it also has a Z sum. That's all that's known. It probably has a Z infinity summoned, and it might just be Z infinity, but we don't know if it has any torsion or anything like that.
Z infinity is a direct sum?
Yes. Okay, so right. So let's consider now. So let's consider the following sequence. I'm going to denote by star. It's a short exact sequence. 0 goes to kernel of mu, goes to theta pH, goes to sigma 2 by mu, goes to 0. And when you have a short exact sequence of groups, you get a long exact sequence in cohomology. So let's start with H4 of theta pH. So this is where this element, the solid one element C of K lives. But mu takes it to H4 of M sigma. And then we have some connecting homomorphism to H5 of M kernel of mu. So it turns out that the image of C of K in here is exactly delta of M. So this is the Kirby-Lieberman obstruction to piecewise linear structures. So recall I said that for every topological manifold, you can define some element in the fourth cohomology that tells you if it's PL or not. And this is, if M has a triangulation, I mean it might not, but if it does, then this is probably the simplest definition of this element. You just look at the links, and you apply the Rocklin homomorphism to all the links, and that gives you this element. By the way, if the triangulation itself is PL, then this element is 0, right? Because all the links are just the 3s here. And what it says is if you, when you apply mu to it, you get 0, then you can find some other triangulation that's PL on the same manifold. So this kind of, governs that question. But this sequence also tells you more. It tells you, it tells you some obstruction for the manifold to have a triangulation, because if it does, if K exists, then delta of M is the image of this, and that means that it gets mapped to 0 here. So one thing that we see from this, I think. Yes, if M is triangulable, then delta of M is 0. And in fact, it's even already. So the converse is harder, so this is the work I mentioned. I mean, it's part of the theory of Galewski-Stern and Matumoto from the 70s. So this tells you this issue of obstruction in triangulations. However, this didn't quite answer the second question, because there is still can this ever be non-zero? That's the question. So now we're translating into that question. And, well, one way in which this would be zero is if delta were zero. And, well, this is a connecting homomorphism. So when you go from short exact to long exact sequences, the connecting homomorphism is always zero in one case when the sequence splits. I mean, that's a sufficient condition. So if there exists some splitting, so a map from Z-map 2 to here, such that when you compose it, you get 1. So if the sequence splits, so what does it mean that it splits? So explicitly, it means that we can find an element. So the image of 1 is some element y in theta 3h, such that mu of y is 1, and 2 of y is 0, right? So y has to be the image of something in Z-map 2, so 2y has to be 0. So if there exists such an element, then just by algebra, it turns out that delta is 0. So all manifolds would be triangulable. This is not the case. But there's even only if, also due to Galewski-Stern and Matumoto. So as part of their theory, they prove the converse. So if all manifolds are triangulable, then this splits. So alright. So how does that work? Basically, so they found some actual manifold that I don't want to describe, but it's explicit, more or less. Well, it's there. There is an actual manifold. It has the property that basically the first Steenrod square of delta m is non-zero. Let me not explain what this is, for reasons of time. But basically, if this is true and if one knew that star does not split, then that would mean that delta of delta m is non-zero. So m is not triangular. And also, once you find m in dimension 5, you can also do m times chloride, m times Tn minus 5, and that's a counterexample in any dimension, at least 5. So, so basically this was the reduction to 3 plus 1 dimensions. It also, it all boils down to the question of this, of the existence of this one. So, so this is just a question about, 3 plus 1 dimensional manifolds. So it's about the homology cobordism group and about the Rothring homomorphism and the existence of torsion of order Q in this group. Okay, so the answer is that it does not exist. So that's a theorem cipher. Such a y does not exist. So the sequence does not. Okay, so let's. Right. So next.
Do you use both hypotheses?
Yes, I do. Yes. So it's still not known if there exists two torsion. Any other questions? So now I'm going to switch gears. So this was like topology, algebraic topology, and now I'm going to go to gauge theory. Right, so we need some tools for studying homological Gordism, and the first tools came from Yang-Mills theory, but then people developed Seiberg-Witten theory. So this is this is somewhat of a TQFT. It's not exactly a TQFT, but TQFT is a topological quantum field theory. It's something that can be used for studying manifolds in dimension 3+1. So, so in dimension 3, there is something called monopole or Seiberg-Witten. Let me just say Seiberg-Witten for homology. There are different variants of this, so and there are different constructions. So there's one, the best known one and the most complete, which is from homeomorphic. There is a different construction by Kirchhoff, and there is one by myself. Yes. So in one version, let me just explain my version. So, for homology spheres, so let's just focus on homology spheres. Actually, they're all the same. So let's just, the formal structure is the same. So let me call this, there is some, group that you get out of studying this. So there are the Seiberg-Witten equations that you study on Y manifolds. So this is a set of partial differential equations that you can write on 4 manifolds, and in particular on cylinders. And from this you form an abelian group. In fact, it's a module. So the Seiberg-Witten equations have some symmetry. So there is. Let me just say this. So they are for a pair A and phi, where this is a connection, and this is some section of a bundle, section of a complex bundle. It's a spinor, and there is an S1 action. That's the important thing. So they have an S1 symmetry. It just acts, since this is a complex bundle, it acts on C, and it's a constant. So everything that you get out of it is going to have this S1 symmetry. In particular, so you can define this as an equivariant theory. So this is the S1 equivariant theory. And this is similar to equivariant homology, which again is not something that I want to get into, but it has more structure than just being an abelian group. So this is a module over some group that's associated to S1. And let's just use Z mod 2 coefficients. So let's use Z mod 2 coefficients. So this is the classifying space of S1. This is just a polynomial ring in one variable, where the degree of U is 2, but since we're doing homology, it goes down, so it acts by decreasing the degree by 2. So you get some module over a polynomial ring. And this is a good tool for studying covordisms, because let's see, where should I put this? Let me put it here. Well, So what is the TQFT property is that if you have a cobordism, you get a map between the Seiberg-Witten homology of Y1 and the Seiberg-Witten homology of Y2. So this is an SU multiplier. So this you obtain by studying the Seiberg-Witten equations on W. So from these four manifolds with boundary.
The test was C2.
Oh yes, sorry, yes. I think I'm going. Yes, that's okay. By which I mean Zima. Okay. All right, so let's see. Actually, I realized I forgot to say something. So I forgot to say what is the strategy of the proof. So let's do that first. So the strategy of proof is going to be, we're going to find a lift. So the Rockland of the Rockland map, this goes to Z, we're going to lift it to Z instead of Z. So we're going to find a map, beta, from theta pH to Z. So beta, interestingly, is not going to be a homomorphism. But it would be nice if it were, but it's not, but that's okay. But it's going to be a map like this with the following properties. Just beta mod 2 is mu, and beta of minus y is minus beta of y. So it's at least that much of a homomorphism. It behaves nicely with respect to minus. So if you have such a beta, so this is an old idea, but this shows that such a y does not exist. So there is no y. I mean, if there was y as before, as here, then, we look at beta of y, right? So beta of y, on the one hand, it has to be odd. But on the other hand, 2y equals 0 means that y is equivalent to minus y. So that means that beta of y is minus beta of y, so beta of y is 0. So that's a contradiction. So, right, so this question is basically, yes, it's pretty much the same as lifting the Rockling homomorphism to Z by a map that has this property. Okay, so the question is to construct maps from theta 3h to Z, and this is what Seiberg-Witten theory allows us to do. So let's see how that goes. So the first map that has some of these properties was found by Freushoff, so he constructed a map that he called H, but I'm going to call delta, from theta 3h to Z. And this is a homomorphism. It's a surjective homomorphism, but yes, delta mod 2 is not. So it doesn't quite solve the problem, but it tells you something called theta pH. So at least it tells you that this is how it was shown that theta pH has a Z. I mean, it's an easy corollary that this has a Z sum. If it has a surjective homomorphism. So the way he did it is he looked at this structure and yes, and he basically noticed that the way this works is that you have some that the Seiberg-Witten homology looks like this. There is an infinite power, and there's some finite stuff. So, as a module. So this tower comes from, basically from the trivial solution to the Seiberg-Witten equations, the equivariant homology of a point, and then there's some other finite stuff from irreducible solutions. And the minimal degree here is basically, the minimal degree in this tower is this 2 delta. So that's how you define delta. And then what you prove is that if you have a homology cobordism, so this gives you, for every y, it gives you this delta of y. But now the homology cobordism, so if you have a homology cobordism W from y1 to y2, then it turns out that you have this induces a map like this, and you can also consider it in the opposite direction. So you get maps back and forth that preserve the towers. So you just have to check what happens for the trivial solution, basically. So this tells you that delta of y1 is delta of y2. So by using the module structure and the functoriality under cobordism properties of this homology group, you can obtain this homomorphism. So now the problem is that there's no connection to the Rocklin homomorphism. So the way we can find such a connection is by putting more structure, and that comes from an additional symmetry. So there is an additional symmetry on the Seiberg-Witten equations. Basically, there's a conjugation symmetry together with S1, so plus S1. What this gives you is an action of the group P2. So P2 is a union of two circles. It's S1 union JS1 as a subset of C plus JC, which are the quaternions. Right. So it's a non-commutative group. So the unit circle in here, and then with the usual notation for the quaternions, 1 ijk. It's an extension of Z matrix by S1. And so basically, apart from that action of S1, there is also an action of J. In fact, this is a quaternionic bundle. This was observed a while ago, but the interesting thing is you can define a P into equivariant theory. So this is somewhat non-trivial. It's harder than doing the S1 equivariant version. So this is something that I did. In fact, yes. So with my construction, so from a homology sphere, you actually get a space or a spectrum, the Floer space, and then you can apply any functors you want to it, like just equivariant theory. H star into of S star of y. But there is also a different approach, more recent by Francesco Lin, in which he does more traditional Floer homology to define such a theory. So it turns out that this theory, so this is a module over the course. So instead of this, we have some other group. Is a module module over sigma 2 of Q and P Q cubed, where the degree of Q is minus 1, and the degree of P is minus 4. That's basically by studying this classifying space of 2. Right, so it's a somewhat different module structure, but you have the same factoriality. So what does it look like, this homology? So here we have a tower and some finite stuff. Here we also have a tower, but really it's made of 3 towers, so it's sigma 2, sigma 2, sigma 2, 0, sigma 2, sigma 3, sigma 2. And then as it keeps going, and then you have some finite stuff. And actually you can, so this is the Q action. And this is the Z action. Yeah, so this is periodic mod 4. And these towers can actually end in different degrees. So you could have maybe related by Q. You could have yes, maybe sigma 2 and 0. Maybe the first tower ends here, but then the others end here. So anyway, you get all this structure. It turns out that the thing that works is the middle tower. So beta is kind of the minimal degree of the middle tower with some normalization, minus 1. And the minimal degrees, so they have the same properties as before, and you get this map beta from beta kh to sigma 2. And the thing that's new is that beta mod 2 is new. So this is connected to the rounding homomorphism. So let's see. I have a little bit of time. Let me just say in words why you get the connection to the rounding homomorphism here and not there. Okay, maybe I don't want to get too technical, but the minimal degree is actually this is congruent to 2 mu mod 4 in the chain complex. So this is the homology of a chain complex, and in Seiberg-Witten theory you do see the Rockling invariant as the minimal degree of the tower in the chain complex. But then there are some differentials, and those differentials destroy this congruence. But this thing is actually 4 periodic. So the degree of D is 4 instead of 2. So because of the different module structure, it turns out that this congruence gets preserved in homology in the P2 theory, but not in the S1 theory.
I didn't understand what you wrote there. Beta goes to Z2, and then you look at beta mod.
Oh, I'm sorry. Sorry. Yes. Yes, it's a lift of Rockling.
So it's crucial that Y is a homology sphere here, so that only Spencer structures are the trivial ones. That's why you can.
So you can define them for all. Well, I define them for rational homology spheres, but you can define them for other 3 manifolds. It's just that you're going to have more towers, more species structures.
So you still get an N2 action. That's the point I was trying to.
Good point. So you do, but it might switch the species structures, and in that case you don't get anything new. You only get new things for the ones that are preserved, for the spin structures. I wanted to end with some over problems. So let's just do that. So let's recall. So now we know that non-triangulable manifolds exist, but we also know more from the work of Galewski-Stern and Matumoto, is that n is triangulable if and only this obstruction in H5 and kernel of mu is 0. So, question is, what is kernel of mu? And in fact, the theory also gives that if triangulations exist, they are classified by H4 of n kernel. So the main open question is, well, what is, this is just an index to subgroup of theta 3h, so what we really want is, what is theta 3h? This is a hard question, but here are some more, perhaps more realistic open questions. Let me focus on two of them. Does there exist a different map f from theta 3h to z with f mod 2 equals mu, and f is a homomorphism? So my beta was not a homomorphism. If you can find a homomorphism, then that's interesting. That tells you that there wouldn't be any torsion at all of roughly invariant 1 in theta 3h. And it would also tell you that you can replace, yes, let me say this, then this would tell you that you can get an obstruction in H5 and C instead of H5 and kernel of mu. So this is kind of annoying. This obstruction lives in this cohomology, but we don't understand what this group is. If you could find such a homomorphism, there's a simple argument that tells you that you actually there's an equivalent obstruction in just the usual fifth cohomology. And the other question is whether there are, so we have delta. Delta is a homomorphism, but are there more homomorphisms? So is there a surjective homomorphism from theta 3h to z infinity? Forget about the relation to mu, just any homomorphism. If so, then that would mean that there exists a z infinity sum in theta 3h. And these two questions look sort of approachable using these techniques. So out of Seiberg-Witten theory, you get this space, and the Seiberg-Witten for space, and you can apply K-theory or many other things to it, or just this equivariant, being two equivariant theories, and there seems to be a lot of algebraic structure, so it might be possible to answer, but these are still open. So I'll stop there.
So in the argument, the sort of crucial that there's this 5-manifold example where you can use it to show that example would not be triangulable. So in that case, if M is that particular 5-manifold, is this a calculable cohomology group? I mean, despite the fact you don't know kernel mu?
Oh yeah, in that case, it's just yes. So what we know about that manifold is that SQ1 of delta M is just that, and let's see, that's a good question actually. Sort of. I mean, I think you get some element in here. Yes, but I mean, you don't know the group. You get some 3-manifold. I mean, yeah, some.
Do you know the cohomology of H with integer coefficients?
Yeah, that's just. I mean, it's a 5 manifolds, so it's non-orientable. It's 0 in I mean, there are many examples, yes, but all of them have to be non-orientable actually in dimension 5. So, so with Z-ma 2 coefficients is Z-ma 2, and they show that this is the non-trivial element in Z-ma 2. Let's see, so the one example I know, which is not the one that they did at that time, but the more modern one is a mapping torus over something with the intersection form 1, 0, 0, minus 1. So you can find some non-smooth manifold with this intersection form of dimension 4, and then you do the mapping torus where you switch these to an orientation reversing thing. So you can compute the homology there.
So this is a non-simply connected manifold that has the same middle homology as S2 times S2, but it's presumably not.
Yes. No. It's simply connected. It's one of the Friedman examples. It's a topological.
Oh.
It's power of CP2 plus CP2 bar.
Standing constructed is it looks like there's a one cycle visible in the picture. Is that simply connected?
No, the M is simply connected.
Oh, I see.
But actually, it's a CP2 that is in CP bar, right? So
it's the phase CP2 plus
the one that's
it's the one with non-trivial curvy sigma. Yeah, but then when you do the mapping torus, you get something non-orientable. Yeah, so you do an orientation reversing homeomorphism. Yeah, that's not simple.
Okay, let's finish this again.